When you think of a volcano, what comes to mind? Probably a huge mountain just spewing fire, right? But that's just the grand finale. It's the end of this massive, epic story that actually starts deep, deep inside our planet. So let's get into it. Let's find out how they really work. All right, so here's the first big puzzle we gotta solve. The Earth's interior, it's as hot as the surface of the sun. So why isn't the whole thing just a giant ball of molten rock? The answer, in one word, is pressure. Just imagine the sheer weight of the entire planet pushing down. It's squeezing everything so incredibly tight that the rock literally can't melt, even though it's blazing hot. So if you want to get magma, which is, the stuff that fuels volcanoes, you need a way to get around that insane pressure. You need like a geological cheat code. And it turns out Earth has a couple of really clever tricks up its sleeve to get that solid mantle rock to finally melt. And here they are, our two main cheat codes. On one hand, you've got decompression melting. The best analogy, it's like popping the cork on a champagne bottle. Seriously. On the other hand, there's flux melting, which is kind of like when you throw salt on an icy sidewalk. They're totally different methods, but they both get us to the same place, magma. Okay, let's dig into that first one, decompression melting. Picture a blob of super hot but still solid rock from the mantle starting to rise up. As it gets closer to the surface, what happens? The pressure on it gets lighter and lighter. And then there's a tipping point. Suddenly, there's not enough pressure to hold its atoms together in that rigid, solid structure anymore, and bam, it just liquefies. It turns into magma. And the crazy part? No extra heat was added. It was all about taking the pressure off. Now for that second cheat code, flux melting. This one is like pure chemical wizardry. What happens here is that water and other stuff, geologists have a fancy name for them, volatiles, get pushed down into that hot mantle rock. And water is a game changer. It gets in there and acts like a catalyst, basically breaking down the chemical bonds that hold the rock together. This dramatically lowers the rock's melting point. So all of a sudden, this rock is melting at a temperature where just a moment before, it was perfectly happy being solid. Okay, so we've got our two ways to make magma. But what actually kicks these processes off? What's the engine behind it all? Well, it's the tectonic plates. Those massive, continent-sized slabs of crust that are constantly, slowly grinding around on the Earth's surface. They're the ones driving the whole show. And this constant motion of the plates creates three kind of main stages for volcanism. You get volcanoes where plates are pulling apart from each other. Those are divergent boundaries. You get them where plates are crashing into each other, convergent boundaries. And then there's a really cool special case called hotspots, where magma just basically punches a hole right through the middle of a plate, miles away from any edge. So let's take that first one, divergent boundaries. A perfect example is the Mid-Atlantic Ridge. You've got two massive plates, literally ripping apart. This creates a huge gap. And what fills that gap? Hot rock from the mantle rises up, the pressure drops, and, you guessed it, it undergoes decompression melting. It's like this non-stop geological conveyor belt, just churning out brand new seafloor. And in some places, like Iceland, it's actually building new land right before our eyes. All right, now let's flip the script and look at the total opposite, convergent boundaries. This is where plates collide. What happens is a dense oceanic plate gets forced to dive down underneath another plate. It's a process called subduction. As that plate goes deeper and deeper, it gets squeezed so hard that water trapped inside its rocks gets forced out. That water, being lighter, then rises up into the super hot mantle rock sitting right above it. And what does it do? It triggers flux melting. And just like that, you've got a batch of fresh magma. And this whole flux melting thing, it's not some small, localized event. We're talking about a process happening on a massive, planetary scale. It's the engine behind some of the most powerful and, honestly, most dangerous volcanic chains on the entire planet. Think about the Pacific Ring of Fire. That's this process in action, creating this huge arc-shaped string of volcanoes. Okay, so mission accomplished, right? We've made magma. But what happens now? Well, this is where it gets really interesting, because it turns out not all magma is the same. Far from it. Its chemical makeup, and one ingredient in particular, silica, is going to determine everything. How runny it is, how it erupts. You could almost say that every batch of lava has its own unique personality. And it really boils down to two main personalities. First, you've got mafic magma. This is the stuff that often comes from decompression melting. It's low in silica, which makes it really runny and fluid, almost like honey.
Because it's so runny, gas can bubble out of it super easily. So you get these nice, gentle, flowing eruptions. Then you have felsic magma. This stuff is the opposite. It's packed with silica, often because it's melted some of the surrounding crust. And that makes it thick, sticky, and gooey. It traps all those gases inside, building up pressure like a soda can you've shaken up, leading to crazy, explosive eruptions. So at the end of the day, it's all about these two things. Viscosity, that's just a sciencey word for how thick or runny it is, and how much gas is dissolved in it. And guess what? Both of those things are controlled almost entirely by that one ingredient, silica. Get those two factors right, and you can predict whether you're going to get gentle rivers of lava or a catastrophic explosion that can literally blow a mountain apart. And that personality we talked about, it doesn't just control the eruption, it actually builds the volcano. I mean, literally. Over thousands, even millions of years, the kind of lava that comes out is what sculpts the final shape of the mountain we see. So, if you're dealing with that runny, low silica, mafic lava, think about it. It can't really pile up on itself, right? It just flows and flows, spreading out in these huge, thin sheets across massive distances. Over time, that slow, steady buildup creates these enormous, but very gently sloped, shield volcanoes. The Hawaiian Islands? That's exactly what they are, giant shield volcanoes. But if you've got that sticky, high silica lava, oh, it's a completely different story. It's so thick and goopy it can barely move. It just kind of piles up right around the vent. And remember, these are the explosive ones, so they're also throwing out tons of ash and rock. It's this combination of thick lava flows and layers of ash that builds those classic, steep, cone-shaped volcanoes we all draw as kids. Think Mount Fuji or Mount Rainier. Those are stratovolcanoes. In fact, that's why they're also called composite volcanoes. It's because they're a composite of different materials. If you could somehow slice one right down the middle, you'd see these beautiful alternating layers. A layer of hardened lava, then a layer of ash, which is called tephra, then more lava, then more tephra. It's like a giant geological layer cake, and that's what gives them their classic, strong, conical shape. Okay, so we've got a handle on how they're made and why they look the way they do. But let's pull the camera back a bit and think about their impact on us, on the planet. Volcanoes are, without a doubt, one of the most powerful forces on Earth, and they have this incredible dual nature. They are forces of unbelievable destruction, but also, amazingly, of creation. And when we talk about destruction, it's hard to even comprehend the scale. A single big eruption can literally change the entire planet's climate. Take the eruption of Mount Tambora back in 1815. It shot so much ash and gas way up into the stratosphere that it blocked out sunlight and cooled the whole globe. The following year, 1816, was famously known as the year without a summer, all from one volcano. And that's not even the biggest they can get. The scale can become truly mind-boggling. A supervolcano. I mean, we're talking about an eruption that can blast out over 1,000 cubic kilometers of material. 1,000. To put that in perspective, that's enough rock and ash to bury a huge chunk of a continent, trigger a global volcanic winter, and cause worldwide famines. It's absolutely terrifying. But, out of all that destruction comes creation. It's an amazing paradox. That same volcanic ash that can choke the skies eventually breaks down and creates some of the most incredibly fertile soil on the entire planet. That's why, throughout history, you see so many people living right in the shadow of volcanoes. And it's not just soil. They bring the Earth's inner heat up close to us, giving us a powerful source of clean energy, geothermal power. So the next time you see a picture of a volcano, try not to see it as just some ticking time bomb, a random disaster waiting to happen. Instead, see it for what it truly is, a fundamental part of our planet's engine. It's a force that has literally built the ground we walk on, shaped our climate, and even helped create the air we breathe. It's been doing this for billions of years, and it's not stopping anytime soon. Which leaves us with one big, fascinating question. What's its next act going to be?